Hey everyone, welcome to Code Harmony. Today we are going to solve LeetCode problem ID 1261. Find elements in a contaminated binary tree. This question has been asked in Google and Amazon, and it's an important tree question. You definitely have to solve it. Based out of tree, but not medium. It is marked as medium, but don't worry, it is going to be very easy once you understand the problem statement. Let's understand whatever given in the problem statement. See, they are saying that given a binary tree with the following rules. Binary tree is following these two rules. Root value is 0 and all the other nodes is based out of the tree value. If the tree value is x, then the left child is 2 into x plus 1. If any value is x, then the right child of that x value is 2 into x plus 2. So this is the rule this binary tree is following. Okay, initially it was the state. Then something happened and this binary tree got contaminated. It means all the values has been changed to -1. So this was the initial binary tree, then it got contaminated, and then again we have to do something. We have to implement this find elements class where we have to do two things. Find elements, this is a constructor, initializes the object and with a contaminated binary tree and recovers it. Okay. So this is our class constructor and this is just recovering the tree. Apart from that, there is a find function as well. Find function is going to return true if the target value is present in the tree, otherwise return false. Okay, so let me explain in a simple manner. See, initially this was the state that we were having a binary tree where the root value is 0, right? Root value is starting value is 0 or any other value, let's say that is x. Then left child should be 2 into x plus 1 and right child should be 2 into x plus 2. See, whenever we carry a binary tree, what we require? We just require a root value. Root value, if we have the root value, we have the whole binary tree. Okay, then this was the initial state. Then something happened and this tree got contaminated and this tree value has been converted to -1. Okay, now this is the tree, contaminated tree. And what we have to do now? We have to implement a class, design a class or design a data structure, you can say, which is going to firstly recover the binary tree and second going to answer our find queries. That's all about the problem statement. Here, if we also have a look on this example, if we try to convert this example in a real binary tree, it will look like this. See, root value is always 0. Root value is 0. Left child is 2 into x plus 1 and the right child is 2 into x plus 2. In this case, there is no root left child, only right child is there. So right child is 2 into 0 plus 2, which is 2. And the left child of 2 is 2 into 2 plus 1, which is 5. And the left child of 5 is 2 into 5 plus 1, which is 11. So this tree will be converted to this tree, and after that, see, first step is done. We have recovered the binary tree, and the second step is find queries. I will just get queries like find 2, whether 2 is present in this tree or not. Yeah, it is present. Yes. Find 5. Yes, 5 is also present. Find 7. 7 is not present, so return false. So just true false result we have to return for the queries. Okay, that's the whole statement. Initially the tree was something like this, then it got contaminated. What we have to do is, we have to first recover the binary tree. We are getting this tree and we have to recover it. Okay, recover this tree in the constructor. It means only one time we are going to do that. After that, the find queries. Find queries is something we are getting a value and then we have to return whether that value is present in the tree or not. Here the problem statement is over. Now let me ask you that see, this is the tree structure, -1, -1, -1. This is the tree we are going to get. It means we are going to get the root value of this in our class, and then using this root value we have to recover this tree. If we are going to recover this tree, first of all we are going to recover this root, then the left child, there is no left child, then the right child is 2 into 0 plus 2, which is also 2, and this is 5 and this is 11. Okay, It means we are traversing every node once, right? We are going through every node once and we are assigning it to the relevant value. In short, if I say we are doing tree traversal, or you can say binary tree traversal, and there are two famous ways for the traversing. First one is DFS, second one is BFS. DFS means using recursion, going into the depth of the current call, and then exploring the next call. BFS is something keep going in the breadth first manner, like for first of all the neighbors, and then neighbors of those second connection, third connection, like this. So it's totally up to you. Whatever way you want to choose, you can choose. In short, we have to do the tree traversal. Tree traversal we are going to do, but let me just ask you first, what is the time complexity of tree traversal? If we are visiting every single node once and the tree is going to have n number of nodes, what is the time complexity? Order of n, right? Because we are visiting every single node only once. So this tree traversal is going to take order of n time, but we are getting an intuition that using this tree traversal, we can somehow recover this tree. How we can recover this tree? Because we are already aware that the root dot value is always 0 and all the other values are 2 into x plus 1 for the left child, 2 into x plus 2 for the right child, right? So these two values we can follow while we are doing iteration over this tree. 2 into x plus 1, 2 into x plus 2. Okay, got it. And in the constant, if something is related to the recovering tree value, initially all the values are -1. Okay. Total number of nodes is in between this, and the height of the binary tree is less than equal to 20. Okay, that's fine. See, this is something we have to do, and let's say if I have to recover this binary tree, then I'm getting some tree in our function. Let me implement the same class as well. Find elements. See, the class is find elements, and the find elements is going to take tree node root, and it is a constructor not doing anything. So let me call a solution function which is going to recover this binary tree, and while recovering this binary tree we just have to make a iteration or traversal. Traversal means just get the root value, and along with the root value I am also going to pass one more variable, which is the value of the current node. Because if it is root, I know the value of the current node. Current node is 0 initially, and later on for the subsequent call I can create the value. For the left child of the root it's 1, right child of the root it's 2, and so on, right? So if you try to see, this is root and this is 0. Let me write it clearly. I'm not going to return anything from this function. First of all, if the root is null, then what we have to do is, we don't have to do anything. It's a terminating case. If root is null, just terminate. Otherwise, assign the correct value to the correct node. Correct node is root, and correct value is this. Initially it is 0. So root dot value is equal to value, assigning the correct value. And now you just go through the left child and right child only if they are not null. Or you can say there is no need to apply the condition, just go to the left child, go to the right child. Solution root dot left. Root dot left, and what is the value of left? 2 into value plus 1. And now solution subcall root dot right, 2 into x plus 1. That's all. We have done the binary tree traversal using DFS, and this traversal is going to take order of n time, but while doing the traversal it is going to assign the exact value to the current node, right? Now that's all. We just have recovered the binary tree, and we were expected to have two steps: recovering binary tree took order of n time, and definitely it is going to be only one time operation. But what about the find queries? In the constraints, they are also saying that the total number of find queries will be in between 1 to 10 power 4. So maximum 10 power 4 number of find queries we can have. So my first step was recovering binary tree. That is done. Order of n time. At least we have to go to every node, and we are just going giving order of n time. So we can't do better than this. So that is fine. Only one time it is there because it was in the constructor. And now the find is a separate function, and find query is something whether the target is present in the binary tree or not. Yes or no. For that, let's say this binary tree is given to you. If you have to search an element in the binary tree, then searching takes how much time? Order of n time. Searching means checking every single element in the binary tree. If checking every single element in the binary tree will go order of n time, but they are saying that we can have a 10 power 4 number of find calls. See, if someone is asking me whether this element is present in the binary tree, this element is present in the binary tree, number of queries we are getting. If we are getting so many queries, we have to do it efficiently. We have to think of some kind of pre-processing. Pre-processing we have to do, and after this pre-processing, if we are getting some better result, we will just improve the average time for per query by doing this pre-processing. This find query is whether the element is present in the tree or not. Okay, if I was having only one query, I would have done it in the order of n time, just doing one iteration. But we can have 10 power 4 number of queries. So see, when you were recovering a binary tree, you are assigning a value. You know how many, what are all the values which are present in the binary tree. See, at this iteration, you are the only one who is assigning the value to the binary tree. So you know what are all the values present in the binary tree. So in case if you maintain some kind of set where you are just going to capture every single value. So let's say in this case, if when you are creating or recovering this binary tree, if you capture what are all the values that you have filled in this binary tree, you can maintain it in a set, right? So recovering took order of n time, and we can utilize this order of n time to save our set, hash set. Hash set means hash set which is going to have all the elements from the binary tree, and taking a value, getting a value or finding a value in the hash set is order of one time operation. Okay. So when we are recovering the binary tree, we are doing order of n time, and again within this order of n time we are storing all the values in a set. And when it is the time of finding queries, we can just directly say whether this set contains this value or not, or set dot contains key, hash set dot contains a target, or you can say key. This operation is order of one time because we are utilizing concept of hash table in this. If you use Java, there you might find a hash set, which is an implementation based out of hash table. So using hash table data structure, you were able to optimize the time for finding queries to order of one time. So now recovering is going to be only one time, and that is order of n operation. Finding queries can go till 10 power 5, but every time it is order of 1. So 1 into 10 power 4. So it is order of 1 per query, right? So this is the best time and the space we can get, and now we just implement it. If you want to do it with the BFS, you can try that by your own. That is also fine. Both are same thing. Let's start writing the code for this approach. First of all, we have to recover this binary tree. And how do I recover this binary tree? By using a helper function root. I also need to pass a value. Initial value is 0. 0 is going to be the value for my root. Okay, I have recovered this binary tree. Firstly, let's just try to recover it. And private void solution tree node root, and along with that int value. What is my terminating case? If root is equal to null, just have to return null. Otherwise, do something and then go for the left tree. Root dot left and solution root dot right. This is the standard DFS function that we write. And for the left and for the right, we have to prepare the value of root. Currently, current root dot value is my value, and this is 2 into value plus 1. And for the right child, 2 into value plus 2. This for the right child. Okay. Do I have to do anything else apart from that? No, I don't see anything. This solution is something which is going to help us recover this binary tree. Okay. Now I can say that this tree is recovered and we have to implement the find query. Find query is something whether that element is present in the tree or not. See, these values are present in the tree. Only these values. So somewhere if I just maintain some kind of set dot add this value. Okay, I can directly check in the order of one time whether the value is present in the tree or not. For that I have to take a set of integer and let's call it set, and this set should be initialized in the constructor. Set is equal to new hash set. Okay, new hash set is this. And what about find query? Whether this set contains the target or not, that's all. Let me run sample test cases. Sample test cases are passed. I'm submitting the problem now. It got submitted successfully. I hope you understood the approach. It's a very easy tree question and good for practicing tree. Thank you guys. Bye bye.